don't want something that's a watch gear pitch if you've got high torque on it. Also, you take a look at what shaft bore or shaft diameter is available in those. Sometimes you pick out a gear for its gear reduction size or the right gear ratio, and you find that it doesn't have isn't available in the shaft bore that you're looking for. So you either have to machine it, bore it out to a larger, or pick a different selection of gears. I personally like the Boston Gear website. You can go in, you can get CAD models for all of their gears. It's got an online system where you send in and it emails you back the CAD model. It's available where you can pull it right into Inventor. And so you're not putting in representations, simple representations. You actually have the gears that you can pull into that. Martin Gear is another good source. I don't believe that Martin has the CAD models. Both of them have good design guides. If you want to do gear designs, go pull those, read through them. There's some great information in there. Timing belts. Timing belts are great, lightweight solutions for drive systems. Here again, pick the right profile for your job. 2 years ago, we used timing belts for our main drive for the base, and we used an XL drive belt for that. We had problems with it slipping. This is one of the timing belts off of our drive, and you'll find that about 80% of the teeth are missing off of this. We just stripped them right off. So, had we used something like the GT2 or the GT, we probably would have been a better selection for the drive system. So, here again, go in, do a little bit of research, take a look at the different timing belt profiles, figure out what's the right one for your application. If you're not using a high torque, the XL probably would have been just fine. But for our application, I think the GT would have been better. As I recall, Bellevue High School used the GT last year for their drive bays, and I think it worked out very well for them. So, first thing is from a weight, you can tell that's going to be much lighter than a chain. The other advantage is you can find aluminum sprockets in many different sizes also. So not only are you saving the weight from the chain, you're saving a huge amount of weight from the sprockets. Like Boston Gear, SDP or Stock Drive Products they've got CAD models for all their products. They've got a really easy belt length calculator to put in to tell you what length of belt you should select based on the diameter of the sprocket you're using and the distance between the hubs. And both Gates and SDP have good design guides. Go in, pull them down if you're thinking about using that. Last year in the kit of parts, they gave us some GT pulleys or sprockets as well as some drive belts. They're actually GT2. And I think last year they also provided a decent design guide as part of that. It was a series about 20 pages on how to use the product. So, timing belts have some real application with robotics. You just have to make sure that you're using them for the right application. Chains and sprockets. The two most common sizes for FRC robots are either a 25 or a 35. I've used both of them for drive systems. I personally prefer the 35. It's a little heavier. We had some problems with chain brake using 25. Get and keep the slack out of your drivetrain. Design in a way of tensioning your chains and sprockets, or your chains. Wind up or slack will cause high stress in the chain and can cause break. So if you don't have the slack out of it and you hit it with some torque or hit it with an impact load, chances are you're going to break that chain if you're using a smaller. So keep the slack out and you'll have a much better design. The other thing is that wind up, you'll lose accuracy. If you're using an encoder to count position of something and you've got slack in there, you're going to have a pretty wide variation on your positional placement. Martin Gear has a good design guide. We tried to go back through Martin Gear and Boston Gear directly to buy gears last year. They don't sell directly to you. However, you go to Motion Industries or McMaster Car or MSC, you can buy it through them. Both MSC and McMaster Car have catalog, so they only have certain sizes of it. You go back through Motion Industries and give them a part number and tell them you don't care if this is a Martin Gear part number, but you don't care if it's Martin or if it's Boston or whoever, and they'll go find you the gear and get it shipped to you. Any questions on gears, timing belts, etc. before I move on? Bushings and bearings. Okay, what's the difference between a bushing and a bearing? Generally speaking, a bushing is a non-moving, it's an annular surface. A lot of times that you got a shaft that goes through, or you can have a thrust washer, thrust bearing, which looks like a washer, and it's for movement around the face on it. But it's usually made out of a metal, something like a bronze oilite, or a metal that's permanently lubricated. Its application is largely for slow speed rotation, maybe not high stress. It's a good way of ensuring that you've got smooth movement through that shaft, but I wouldn't use it in a high strength, high stress, or high speed rotation. Bearings are similar in application. You'll find it on the wheels. You'll find it on a lot of different moving surfaces. Here you've got an inner race. You've got a whole series of ball bearings that go all around it. And then you've got an outer race. And so it is extremely low friction. You've got a hardened inner race and outer race. Ball bearings are recommended over bushings. Frankly, I prefer sealed bearings, which means that they've got a cover over the ball bearing so that you can't get trash and debris down there, which will just can destroy your bearings. I also have a flange on it. Looking at the side view of it, have a flange. Here's your axis through it. So when you machine your plate that you want that to go in, you machine it to this diameter. You push it in to where the plate sits in there. So it's a positive way of keeping it in place and in position and keeping it concentric with your shaft. Okay? Lead screw. One of the robots that are out in the commons area has an elevator mechanism on it that's at an angle, and the way that they move the elevator up and down is through a lead screw. So it looks like in that case, it was like a 4-foot long diameter threaded rod. Put a motor on one end. You're turning that rod, which drives the up and down movement on the elevator.